Hello my dear students, today we are going to learn about group 15 elements or nitrogen family. Group 15 elements include nitrogen, phosphorus, arsenic, antimony, bismuth and moscovium. Some of the nitrogen family members are known in earlier times. Others are discovered by the following scientists in the respective years. We know nitrogen is the most abundant component of the Earth's atmosphere. The element also exists in the Earth's crust as sodium nitrate and potassium nitrate, as Chile saltpeter and Indian saltpeter. Phosphorus occurs in various orthophosphate minerals. Arsenic, antimony, and bismuth occur in lower total abundance, mainly as sulfide minerals. Now we can learn some aspects of general characteristics of group 15 elements. This include electronic configuration, atomic radii, ionization energy, electronegativity, metallic character, oxidation state, allotropy and atomicity. The valence shell electronic configuration of group 15 elements is ns2np3. On moving down the group, atomic radius increases. We know the radius of an atom is governed by two factors, the number of shells of electrons around the nucleus and the attraction of the outer electrons field from the nucleus. The attraction of the outer electron field from the nucleus depends on the shielding effect. That is, electron between the nucleus and the valence electrons repel each other and making the atom larger. We know as we move down the group, nuclear charge increases, number of shells increases in each step, causing the valence electron to be farther from the nucleus, and shielding effect of the inner electrons increases down the group. The combined effect of increase in number of shells and shielding effect outweighs the shrinking effect caused by increased nuclear charge. So atomic size increases on moving down the group. There is a considerable increase in atomic radius from nitrogen to phosphorus. This is due to the strong shielding effect of inner s and p electrons in phosphorus. Whereas in the case of arsenic, antimony and bismuth, there is only a small increase in atomic radius from arsenic to bismuth. This is due to the poor shielding effect of inner d electrons in arsenic and antimony and inner f and d electrons in bismuth. That is, the increased nuclear charge is more felt on the outer electrons of arsenic, antimony and bismuth, and therefore the increase in atomic size is less significant. The next general property is ionization energy. We know ionization energy is governed by three factors: the charge on the nucleus, the amount of screening by the inner electrons, and the distance between the outer electrons and the nucleus. As we move down the group, nuclear charge increases, atomic size increases, and the screening effect increases. The combined effect of increase in atomic size and screening effect outweighs the shrinking effect caused by increased nuclear charge. So, ionization energy decreases on moving down the group. That is, the ionization energy decreases down the group due to gradual increase in atomic size. Because of the presence of the highly stable ns2np3 electronic configuration with half-filled p orbitals and due to smaller size, the ionization energies of the group 15 elements are much greater than those of group 14 elements in the corresponding periods. The sharp decrease in ionization energy from nitrogen to phosphorus is due to appreciable increase in atomic size and the screening effect of the s and p electrons of the penultimate shell in phosphorus. Due to the poor shielding effect offered by the inner d electrons of arsenic and antimony, as well as the penultimate shell of d and f electrons in bismuth, nuclear attraction is considerably felt on the outermost electron. As a result, the increase in atomic size down the group from phosphorus to bismuth is not of very great magnitude. So, the decrease in ionization energy from phosphorus to bismuth is also not very great. Next general property is electronegativity. As we move down the group, electronegativity decreases from nitrogen to phosphorus due to significant increase in atomic size. The increase in atomic size from phosphorus to bismuth is not very significant, so there occurs no significant change in electronegativity. The next general property is metallic character. As we move down the group, ionization energy decreases and metallic character increases. Thus, nitrogen and phosphorus are nonmetals, arsenic and antimony are metalloids, whereas bismuth is a metal. The next general characteristics is oxidation state. A variety of oxidation states are shown by group 15 elements. We know the valence shell electronic configuration of group 15 elements is ns2np3. So, the common oxidation state of these elements are -3, +3 and +5. The first element nitrogen exhibits several oxidation states -3 to +5. This ability of nitrogen to show such a variety of oxidation state is due to its small size, high electronegativity and a strong tendency to form p-pi bonds. These are some examples of nitrogen compounds in which they show the respective oxidation states. Group 15 elements show negative oxidation state. These elements has 5 electrons in the valence shell, that is the outer electronic configuration is ns2np3 and require 3 more electrons to acquire nearest noble gas configuration. But gain of 3 electrons is energetically not favored. But since nitrogen is most electronegative element and the smallest atom, it forms nitride ion by gaining 3 electrons. Other elements form covalent compounds with metals and show an oxidation state of -3 with the metals. The tendency of elements to exhibit -3 oxidation state decreases on moving down the group from phosphorus to bismuth. All elements show positive oxidation state from +3 and +5 on moving down the group. Stability of +5 oxidation state decrease while that of +3 increase due to inert pair effect. The inability of inner s electrons to take part in bonding is called inert pair effect. Because all elements cannot lose all 5 valence electrons, they do not form M5+ ions, and all compounds of group 15 having +5 oxidation state are covalent compounds. Nitrogen exhibit positive oxidation state +1 to +5. The oxidation state from +1 to +4 tend to disproportionate in acid solution. For example, nitrous acid converts into nitric acid and nitric oxide. Phosphorus can show +1, +3, +4 and +5 oxidation state in some oxo acids. All the oxidation state intermediate between +5 and -3 tend to disproportionate into +5 and -3 both in alkali and acid. For example, phosphorus acid converted into phosphonic acid and phosphine. However, the +3 oxidation state in arsenic, antimony and bismuth become increasingly stable with respect to disproportionation because of inert pair effect. Phosphorus is able to form its pentahalides, but nitrogen is not. Why? The maximum covalency of nitrogen is 4 because it does not have vacant d orbitals in its valence shell. But all other elements have vacant d orbitals and can show covalency of 5 or 6. The next general property is allotropy. Allotropy is the existence of 2 or more different physical forms of a chemical element. There are 2 allotropes for nitrogen, alpha and beta nitrogen. That is cubic nitrogen and hexagonal nitrogen. Allotropes of phosphorus are white phosphorus, red phosphorus, black phosphorus, scarlet phosphorus, violet phosphorus, etc. The allotropes of arsenic are yellow, black and grey arsenic. Allotropes of antimony are yellow and grey. The next general property is atomicity, physical state and elemental structure. Atomicity is defined as the total number of atoms that constitute a molecule. Nitrogen exists as a diatomic molecule. Nitrogen is gas and other group 15 elements are solid at ordinary temperature. Nitrogen forms a diatomic molecule, whereas phosphorus, antimony and arsenic forms P4, sp4 and as4 units. Why? Due to significant repulsion from the non-bonding electrons of the penultimate shell, their atoms cannot approach each other sufficiently close to cause effective p-pi bonds through sidewise orbital overlaps. They form giant lattices, and the bonding in these lattices gradually changes from covalent to metallic on moving down the group. As a result, the formation of diatomic molecule is much less favored. White phosphorus is a white translucent waxy solid with a garlic smell. It consists of discrete tetrahedral P4 molecule. The PPP bond angle is 60 degree. It is least stable and more reactive due to angular strain. It readily catches fire in air and must be stored under water for safekeeping to prevent it from catching fire spontaneously in the air. Red phosphorus is polymeric and it is obtained by heating white phosphorus at 673 Kelvin. It consists of chains of tetrahedral P4 units linked together. It is more stable and less reactive than white phosphorus. Violet phosphorus is obtained by heating red phosphorus in a sealed tube at 530 degrees Celsius. Black phosphorus is the most stable form. It has a layered structure and is a highly polymerized form of phosphorus. There are two types of black phosphorus, beta and alpha. Beta black phosphorus is obtained by heating white phosphorus. Alpha black phosphorus is obtained by heating red phosphorus. Beta black phosphorus consists of corrugated sheets that results in the formation of flaky layered crystals. Alpha black phosphorus is opaque monoclinic or rhombohedral crystals. Beta black phosphorus conduct electricity, whereas alpha black phosphorus does not conduct electricity. Today we have learned about some aspects of general characteristics of group 15 elements. In the next part, we will discuss about hydrates of group 15. Thank you.